sequence is an ordered list. It's just simply a pattern. It's an ordered list. In this particular case, the pattern is what? Since we're having each successive term, this is a special kind of sequence. Do you know what it's called?
Recursive.
Geometric is a sequence where each successive term is a multiple of the one before it. There's a common multiplier or common ratio. In this case, r equals 1/2. The common ratio. Yeah, come on up. And you guys had some sequences on the last test where you were to read notation and get used to the whole thing about sequences, right? So, have you worked with some of the formulas for geometric sequences and stuff yet? Pretty much? Okay. All right. So what's the difference between that and a series?
A series is adding the sequence together.
Right. So here's how a series would look. Okay? So here's the basic deal with the basic game with series is simply this. If you added the terms forever, would there be a cap on how big the sum will ever get, or will it just keep getting bigger? And so the game we always play is, and this is always how you'll see it written, does the series, which means the sum of all the terms, does that sum converge or diverge? Which basically means, is the sum just going to keep getting bigger, or is the sum going to have a limit to how big it will ever get? And different types of series have sort of different rules that apply, and there are a lot of them. You'll spend a lot of time on this. But I'll give you an example of sort of the picture of how this looks. If we take a look at to me, this kind of helps illustrate what I mean. You don't have to write this down or anything. But this is a geometric series. And if the area, one way to illustrate it is by area. If the area of this piece is 16, and we shade it in, and then the area of this, of course, if I needed to add 8 to that, this piece would have an area of 8. And then if I needed to add 4, this piece would have an area of 4, so I would add that. And the next term, of course, would be 2, so I'd add an area of 2. And then what would the next piece's area be? 1. And so what I'd like you to, this to me illustrates a really important concept. If I did this forever, what would happen? Exactly. Perfect. So here's the deal. If we did this forever, we would never fill the box. You know what I mean? So if we did this forever, an infinite number of terms of a series, does that make sense? The cap on, the limit on how big the series would ever get is 32. So we say this converges, and the sum is 32. And so if this one is special, it's a geometric infinite series. And an infinite series, G sub 1 over 1 minus R, is the sum of how big things will ever get. And so in this case, that would customize to equal the first term over 1 minus 1/2, which is 16 over 1/2, which is 32. So the easiest the easiest infinite series to work with is a geometric. And if you can identify it as geometric, you will know that if this ratio is less than 1 and your terms are getting smaller, it's going to converge to this limit right here. I chose this one because it's simple and it's very easy to illustrate with the area, and then you can kind of have a mental picture of how this works. So what you're always trying to figure out with a series is what type of all the different types, the way I picture it is, well, let's see, is it the type where it'll never get bigger than that? Or is it the type where you're going to end up going, oh yeah, and always adding on a little more and a little more and a little more, and of course this kind of a one would diverge and this kind of a one would converge. So, does that help, or did you already know that? Does that kind of give you a picture? So, there are many types of sequences in series, and classifying them is helpful because we know certain behaviors always exist with telescoping series, geometric series, harmonic. So let me show you a couple different ones. Actually, I should follow. Okay, I said this in words. So I said this in words, but it's important. They only converge when the common multiplier is a fraction, obviously. When they're, so that's kind of important. Okay, that actually was in her notes. Trying to think of what would be most helpful because I'm not familiar with this homework. 7 and 8 are both geometric. Okay, so that makes it easy. So is 9. So is 10. So I'll show you another type. This is one of the most well-known that you'll work with is called harmonic. And you can kind of see the pattern there, right? 1/2, 1/3, 1/4. So here's where the game can get a little bit dicey. This is a sequence, and I want to know what, does this sequence converge or diverge? The sequence. What are the terms doing? Approaching 0. If we graphed it, it would approach the x-axis, and it would. So the sequence converges. In other words, do the terms approach something? Yeah, 0. Okay, perfect. Okay, so then what would the series, this same series, look like? Well, it would be 1/2 plus 1/3 plus 1/4 plus 1/5. And this is one that I'll just tell you, it seems like it should behave like the problem we just did because the terms are approaching 0. So it seems like it should behave that the series converges to a finite sum of how big the total will ever get, but it doesn't. So the quicker you can learn to identify harmonic is one of the known, the series diverges. And I think that it wasn't in her notes, so I may not show you the proof of why that works. But later on you'll learn some improper integrals are one of the things you use to decide if series converge or diverge, because you picture them like these terms are kind of pictured like the function 1/x, and you can analyze kind of the area that